Greetings, welcome and welcome again. Today we move on to module 2 of this course. In the last module, we explained about turbulent flows with some introduction. We took example situation, flow past a building, jet and so on. We also talked about mean velocity and deviation from mean velocity, or instantaneous velocity is decomposed into mean velocity and fluctuation. We also learned a little bit about tensor notation and some algebra. In this module, we will now focus specifically on deriving governing equation for turbulent flows. While deriving equation for turbulent flows, we end up in getting a new term called Reynolds stresses. We will define Reynolds stresses and modeling of Reynolds stress by different procedure. So, this particular module is split into two parts. In the first part, I am going to explain till we get the derivation of the Navier-stokes equation for turbulent force. In part 2, we will get some more details about this Reynolds average Navier-stokes equations and Reynolds stress terms. We will also get to explain about the closure problem. For the sake of completeness, I would like to repeat important information about tensor and notation used. We use subscript I and j, and I and j will take value 1, 2, 3. If the subscript is repeating in a particular term, then it is a summation, otherwise it is each term it is a single term. For example, ui is a particular term, subscript I is repeating. For every value of I you get one term, but then they are summed up, and as you can see here, ui means u1 plus u2 plus u3. If you have a term uj where subscript is not repeating, then for every value of I and j you get new term. For every value of I 1, 2, 3, we have every value of j. So, you get 9 terms in total, and all the 9 terms are listed here as u1, u2, u3. Similarly, the last term u3. u1 is referred for x component of velocity, and u2 is used for y component of velocity v, and u3 is used for z component of velocity w. We also learned a new term called Kronecker delta ij. The Kronecker delta has a value of 1 if I is equal to j, otherwise it is 0. We also represented Kronecker delta in the form of a matrix as shown here 1 0 0 0 1 1 and 0 0 1. So, it is a diagonal matrix. We will now start using index notation in detail, and wherever possible I will repeat information about the index notation. We know there are two main equations, one is a continuity equation, other one is a momentum equation. We will explain in detail how to derive continuity equation for turbulent flow. First, what is shown here is a continuity equation in general. We know for a steady as well as incompressible situation, the continuity equation is written as shown here, that is dou u by dou x plus dou v by dou y plus dou w by dou z. Now, the same continuity equation in the form of an index notation is written here dou u I by dou x I equal to 0. I mentioned if the subscript is repeating in a particular term, it is summation, and in this term I is repeating, one in the numerator, one in the denominator. As I mentioned, I takes a value of 1, 2, 3 and each term is obtained, then they are summed up, and that is what you get here. When you substitute I is equal to 1, you get u or u1 and you get corresponding x direction. I is equal to 2, you get u2 or v and corresponding direction y. I is equal to 3, you get w or u3 and corresponding direction z. So, you understand the easiness. Same continuity equation with 3 terms in the form of index notation is written so concise. Now, we substitute the decomposition. We already learned the flow variable instantaneous quantity can be written as a summation of mean plus deviation from the mean. For example, u instantaneous quantity is written as a sum of mean u bar plus deviation from the mean u prime. Now, we use index notation. It means the decomposition is applied for any particular velocity component u, v, w. So, we substitute this decomposition concept into each term in the above equation, that is u, v, w. That is the meaning of using this index notation I. So, dou u I by dou x I equal to 0. If you substitute u I, which is now in turbulent flow is interpreted as instantaneous quantity. So, dou u I by dou x I equal to 0 continuity equation, it is very generic. When you apply for turbulent flow, you interpret that velocity as an instantaneous velocity. So, dou u I by dou x I equal to 0, you apply the decomposition for the velocity u I as shown here, that is u I bar plus u I prime and divide by dou x I equal to 0. So, you take that separately, that is dou u I bar by dou x I as one component and u I prime as another component. So, if you write down that way, it becomes dou u I bar by dou x I equal to 0. So, this equation, that is equation that is marked as 1, is for instantaneous quantity, and equation that is marked as a 2, that is dou u I bar by dou x I is a mean quantity, and if you subtract 1 minus 2, that is a subtraction you perform, then you get equation based on fluctuating quantity as shown here. So, equation 2 is mean continuity equation, and this particular equation where you use fluctuating quantity is a continuity equation based on fluctuating variable. So, what we have done in this slide, we have written a generic continuity equation in very expanded form, then we write the continuity equation in the index form. When we use continuity equation for turbulent flow, we interpret that u as an instantaneous quantity. We apply the decomposition for the instantaneous quantity as summation of mean plus deviation. So, if you substitute, then you get two separate equation, one based on mean quantity, another one based on fluctuating quantity. In the expanded form, you write dou u prime by dou x plus dou v prime by dou y plus dou w prime by dou z equal to 0. So, you take this equation and look at this equation, that is the initial written continuity equation and final written continuity equation. The format looks the same, that is you have dou by dou x of u plus dou by dou y of v plus dou by dou z of w. We use quantity, one instantaneous, other one mean, other one fluctuating quantity. So, we have continuity equation written in the same form, the variables are interpreted differently for different situation. In the case of laminar flow, it is a plain velocity component. In the case of turbulent flow, we get two separate quantity, one based on mean, another one based on fluctuating quantity. Now, we have to extend this procedure for any other equation to be used in turbulent flow. Minimum you will use momentum equation. If you are having any temperature to be considered, the energy equation, or concentration separately we use species equation. So, for each of this equation we apply this decomposition principle and take an average to get corresponding equation to be used for turbulent flow. Now, let us try doing it for momentum equation. I repeat again, here continuity equation dou u I by dou x I equal to 0, the continuity equation written in the index notation form. Now, momentum equation in the index notation form is shown here. We already know this is otherwise called Navier-stokes equation, dou u I by dou t plus u j dou u I by dou x j equal to minus 1 by rho dou p by dou x I plus nu dou square u I by dou x j dou x j. Now, in this equation u I is only one term. Here again the next term u j dou u I by dou x j. In this term u I appears only once, whereas j index appears more than once, twice. So, for every quantity of j it will be one term, but then they are summed up. That is a rule we learned. If the index is repeating, then it is a summation, otherwise each term single term. So, I is single, for every value of I you get single term, whereas within that I for every value of j you get single term, but they are summed up. Now, let us look at the other term on the right hand side. So, dou p by dou x is a single term. Now, the diffusion term numerator dou square u I is a single term, whereas denominator you have j index repeating. So, you get summation. We already learned Navier-stokes equation in very detailed form. So, this equation if you use index values, then you get this expanded equation of the Navier-stokes equation. So, you can cross check. For example, if you substitute value of I to be 1, then you get x momentum equation, and for every value of I equal to 1 for each term, for example, the second term on the left hand side dou u I is a convection term, and u with the value of I is equal to 1 is u itself, whereas j index is repeating, it is a summation. So, for every value of j you get one new term and then they are added. So, u when j is equal to 1 it is u, when j is equal to 2 it is v, and corresponding x j will be y, when j is equal to 3 it will be a w, and corresponding x j will be z. So, you put them together you get this dou u by dou t plus u into dou u by dou x, v dou u by dou y plus w dou u by dou z. So, we get 3 terms, but they are summed up and u is only 1 for value of I is equal to 1. Now, you can immediately appreciate the advantage of writing with the index notation. In the original tensor notation form it just only one term for convection, and in the expanded form you get 3 different terms. On the right hand side, once again when you substitute value of I is equal to 1, dou p by dou x term appear, and the second term diffusion term dou x j, if you expand j with the value of 1, 2, 3, and because it is repeating its summation you get dou square u by dou x squared plus dou square u by dou y squared plus dou square u by dou z squared. So, this first equation is a x momentum or u momentum equation, and we now repeat for the next value of I, that is 2. So, when you substitute I is equal to 2 in this, then you get V momentum equation or Y momentum equation, and that is what is shown in the next equation. Similarly, if you substitute I is equal to 3, then you get third momentum equation or W momentum equation, that is what is shown on the last equation. So, these 3 equation in this detailed form we are able to write in a very concise form using tensor notation as shown in this equation. I hope by now you are able to appreciate the index notation and understand the way index notation used to write the detailed form of the equation. We already learned turbulent flows exhibit random or variation with the time, and this is a representation, a quantity f as a function of time which shows fluctuation, and we learned continuity equation in tensor form, momentum equation in tensor form. Now, we have to take this equation to turbulent flows. As I mentioned before, this is generic equation. Now, it depends on how we are interpreting for turbulent flow. So, same equation, all these quantities, what are the quantities in this equation? U, and U with the index I 1 to 3 will have 3 variables, that is U, V, W or U 1, U 2, U 3. Then one more variable is pressure P. So, if you interpret all these 4 variables in turbulent flow as an instantaneous quantity, then you apply decomposition to each one of this quantity. We know the decomposition, for example, U I instantaneous decomposed into summation of mean and deviation. So, if you substitute, then we get final Navier-stokes equation to be used for turbulent flows. We learned little bit about tensor algebra, some important information about tensor algebra. There are some more things that we have to do. So, we said time average on the derivative is the same as derivative on the time average. Okay. Now, the second quantity in the Navier-stokes equation on the left hand side is a convection term. It has u j dou by dou x j of u I. Now, what do? We apply decomposition into this. So, if you do a time average, so you get u I bar plus u I prime and then u j bar plus u j prime, and you take a time average on that quantity. Now, why do we do this? Because if you take u j into the derivative, so it becomes dou by dou x j of u I u j. So, you have a product of 2 velocity component. Now, you want to apply decomposition to that product, that is u I u j, you want to apply decomposition. U I is one instantaneous velocity, u j is another instantaneous velocity. So, if you write decomposition for the respective instantaneous velocity, you get u I bar plus u I prime. The second instantaneous velocity u j, you get u j bar plus u j prime, and we perform finally time averaging, and that is what is shown over bar covering both the quantities. Now, we follow some rules. We already listed few rules based on averaging. After following those rules, we are not going to the details. Finally, you get a term as shown here on the right hand side. So, u I bar u j bar, they are product plus u I prime u j prime bar. So, if you write this term, substitute this term for the convection term, you can apply similar steps for each term separately, separately for derivative, separately for pressure, separately for diffusion term, and finally, you get a equation as shown here. In this, I am not showing in detail about steps, it is more important to know the equation and understand terms in the equation. For detailed steps in the derivation, one has to look separately other material. It is slightly beyond scope of present lecture. So, the final equation, after performing decomposition for each variable, following some tensor algebra, performing average, then you get equation as shown here. What is to be noted importantly is first term, for example, is a time derivative term, and this term has the same form as the original Navier-stokes term. Original Navier-stokes equation as a time derivative term, the time averaged Navier-stokes equation also has a time derivative term, and this is u I bar and this is only u I. It is original Navier-stokes equation, as I mentioned, it depends on how you are interpreting for a turbulent flow. The turbulent flow, all these quantities are interpreted as a instantaneous. The second term in the Navier-stokes equation, u j dou u I by dou x j. The second term in the time averaged Navier-stokes equation is u j bar dou u I bar by dou x j. So, you can understand the second term appearance wise it is the same, or the format wise it is the same, both in the original Navier-stokes equation and the averaged Navier-stokes equation. The only difference is the variable. So, in the original Navier-stokes equation it is instantaneous, whereas in the averaged equation it is average quantity. Then you have one new term coming into the picture, that is dou by dou x j of u I prime u j prime bar. This is a new term which is coming after applying decomposition, following tensor algebra, doing an average on the original Navier-stokes equation, then you end up getting one additional term in the time average Navier-stokes equation, and that is what is shown here. Now, come to the right side, pressure derivative term is the same as the pressure derivative term in the original Navier-stokes equation, except that it is now with the time averaged pressure. Similarly, the diffusion term is also same as the original Navier-stokes equation, except that we use now time average quantity in the average Navier-stokes equation. The new term which is shown here, dou by dou x j of u I prime u j prime bar. So, u I prime we know it is a fluctuation and bar is for average. So, this u I prime u j prime bar actually represent action of velocity fluctuations on the mean flow. Why it is mean flow? Because we have written this equation for average, all the terms appear as average, for example, u bar and p bar. The only different term is this fluctuating quantity u I prime u j prime. Now, this quantity u I prime u j prime actually represent velocity fluctuations. You know, individually they represent velocity fluctuation. The relation of velocity fluctuation on the mean flow is actually represented by this particular term. Now, this term u I prime u j prime is a main cause for turbulent flow modeling. In the last slide, when we did the decomposition applied to convection term, we end up getting a term called Reynolds stresses. I did not explain the convection term in detail. In this slide, we will look into the convection term alone in detail. So, convection term is written as shown here, u j dou u I by dou x j equal to dou by dou x j of u I u j. So, what we have done? We have taken the term u j inside the partial derivative, and that is what is appearing here as dou by dou x j of u I u j. Now, we have to explain why this can be done. So, if you actually perform partial derivatives on this variable u I u j by product rule. So, you get first term as u j dou by dou x j of u I plus u I dou by dou x j of u j. So, you perform dou by dou x j on this variable u I u j, apply the product rule principle, then you get two different terms as shown here. Now, if you look at this term carefully, the first term is actual convection term, that is what we have here, u j dou u I by dou x j. So, that is exactly the convection term. The second term we have u I dou u j by dou x j, and dou u j by dou x j actually represent continuity equation. We know for incompressible flow the continuity equation dou u j by dou x j equal to 0. So, because of this, it is possible to write convection term in the form as shown here, dou by dou x j as u I u j. If you substitute decomposition for every velocity variable as u I bar plus u I prime, then we have u I u j written as u I bar plus u I prime and u j bar plus u j prime. Now, you perform the products. So, we have u I bar u j bar for the first term, then u I bar u j prime for the second term, then third term u I prime multiplying u j bar, then u I prime multiplying u j prime. Now, you perform time averaging on this. So, they are shown separately here, u I bar u j bar over bar, u I bar u j prime over bar, u I prime u j bar over bar, u I prime u j prime over bar. Now, we apply what we learned in tensor algebra. So, this time averaging on the fluctuation, and here also time averaging on the fluctuation, these two terms will go to 0. So, we have two terms, that is u I bar u j bar, second term and third term they go to 0, then we have u I prime u j prime bar. So, the first term will be the convection term, but applied for turbulent flows. The last term is the extra term, and that is a Reynolds test term. With this, we come to part 1 of this lecture, then we move on to part 2.